these problems is to figure out which rule you should be following, right? Or reversing. And this one has a square root in it. So the first thing your brain should do would be like, whoa, none of my basic rules have a square root. I need to rewrite that. So here we go. Let's just rewrite the binomial to the 1/2 power. Okay. So we're definitely going to be using a reverse power rule here. So I'm going to write my generic reverse power rule out. So reverse power rule. And you don't have to do this on a test where you write reverse power rule and write it out. I mean, I'm just doing it for teaching purposes. And I suggest you do it when you're doing your homework, just until you get it internalized, what like the requirements are for using this rule. But I'm just going to write it out real quick. Oh, I hear a little chime. There we go. Did I? Oh, it's cubed. Oh, there you go. Thank you. Let's change that. Thank you. Oh, that would have totally messed this up. Thank you. Okay, so we know we need to use this rule, and I just want to emphasize really quickly, because in your homework, in some of the later problems, I threw a problem in that would be like considered an easier problem, but once you see these harder ones, your brain forgets about algebra. So you might be tempted to try to like distribute that monomial in there, but we cannot do that. We cannot distribute this monomial because the binomial is trapped to the 1/2 power. If that had just been a 1, like if there had been no exponent there, then you could distribute it. Then that would be allowed. And it would make this problem a whole lot easier, right? But because that binomial was to the 1/2 power, you cannot distribute the monomial in there. But you should always slow your brain down and think, can I distribute that monomial in? Because if you can, it's a much easier problem. But in this case, we can't distribute it. So we're going to have to do some u substitution here. So I'm going to take my base, and I'm going to make it my u. So this base right here, I'm going to substitute the base to be the u. Oh, I heard a little chime. Rewrite the square root. Rewrite the square root. Oh, sorry, it was in the top. Okay. When I'm in the app, the biggest drawback is I can't see the chat room. So if you ever post something directed like to me and I don't see it, just unmute and you can talk. I should try setting up that other computer again. I just kept getting feedback. Okay, so let's see. So let me get my brain turned on. Okay, so we saw a square root. We knew that wasn't allowed in any of our rules, so we rewrote it as a fractional exponent. We checked to see if we could distribute, but we couldn't distribute. So now we're like, okay, we better do some u substitution. So I'm going to make the base my u. So we're going to let u be this binomial. Okay, and I'm going to come right over here what that's going to look like. So if I do that, I'm going to have 4x squared u to the 1/2 dx. Okay, that's still awful because our variables are all mixed up. I need only u's, right? So I'm going to come over here and take the derivative of this with respect to x. And when we do that, we're going to get 3x squared. And then we're going to move that dx to the other side, right? Technically, you're multiplying both sides by dx. And then we're going to end up with a du cashes in for 3x squared dx. And we have some of those pieces. Let's see what pieces we have. So to get a du, I need a 3, an x squared, and a dx. Let's see what we've got, because we're going to use the idea of use what you have. Well, I have the x squared. I have the dx, but instead of a 3, I have a 4. Well, that's not very helpful. So first of all, that 4, since it's not helping me out, remember we have that rule that says we can pull the 4 out, since it's a constant being multiplied, we can pull it out front. So I'm going to go ahead and do that. I'm going to pull that 4 out in front of my integral. And I'm going to relocate that x squared. I'm just going to rearrange some multiplication. I'm going to pull this x squared back here with this dx. I'm just reordering the multiplication. So I'm kind of grouping all my x's together and all my u's together. So what I'm doing here, and I pulled that 4 out. Okay, So let's think about it. I have my x squared. So I have my x squared. I have my dx. So x squared right there. Dx right there. I need to get rid of that 1/3. So I'm going to divide both sides by 3. And that tells me that a 1/3 du cashes in for an x squared dx. So this x squared dx, this is going to cash in for a 1/3 du. So all of this is going to cash in for a 1/3 du. Okay, so let's go ahead and write that in there. Well, that looks hideous. But that's okay. We can, it's almost matching this reverse power rule up here, right? Almost. There's technically a constant in there that's not matching. So let's just pull that out. Remember, if there's a constant being multiplied, we can pull it out. And so technically you'll have a 4 side by side with a 1/3. So you multiply that on your calculator using your fraction button, or you might just recognize it's 4/3. So when I pull that out, I'm going to get a 4/3 integral u to the 1/2 power du. And that's going to fit my rule. Let's make sure it meets all the requirements here. My exponent is a constant, just like it needs to be in my power rule, right? My exponent needs to be a constant. My base is a plain variable. Just like the base up here, it needs to be a plain variable. And also my my variables match. The variable in the bookend and the variable in the integrand, they match. So we're ready to reverse our rule. But before I do that, let me pause since I'm not able to see your faces. Show me a status. How are you feeling on this idea right now? This idea of this u substitution and pulling out constants, using what you have to do a swap. Okay, I'll go ahead and pause for a minute. I know I was going kind of fast there. Give you a chance to catch up. Okay, now that it's all set up, now that my exponent's a constant, my base is a plain variable, my variables match, now we're ready to just apply this reverse power rule. So let's do it. So I'm going to have a 4/3. That's along for the ride, so don't forget about it. But then when I use my reverse power rule here, I'm going to do my base, increase the exponent by 1, divide that off, plus c. I'm just following my template. So let's clean up those exponents a little bit there. So that's going to be 4/3 u to the 3/2 over 3/2. You can just do that in your calculator if you want, plus c. You could also make it 1.5 if you wanted to use decimals, that's fine. But this is yucky, y'all. So before I unsubstitute, I'm just going to clean this up. I'm going to take my 4/3 and I'm going to divide by the 3/2. So if you type that in your calculator using your fraction button, or if you're using division button, put those in parentheses. If you do that, you'll see 4/3 divided by 3/2. Or if you know how to do it by hand, you'll see that it's just, oops. Oh, it's pretty ugly. Oh, it's still ugly, but at least it's prettier. 4/3 divided by 3/2. I multiply by the reciprocal. Ooh, 8/9. Okay, well, that's ugly. But it's better than 2 fractions, right? 1 fraction is better than 2 fractions. So here we go. So that would be 8/9 u to the 3/2 plus c. And I get all excited and I type that into my math lab and I press enter and it counts it wrong. Why is this wrong? Because we need to unsubstitute that u. You're not done until you get the variable back. That right now I have u's. I originally had x's. I need to get those x's back. So let's go ahead and do that. I'm going to replace the u with a binomial. So I'm really going to get 8/9 binomial to the 3/2 plus c. Okay, I promise to slow down a little bit on the next one. Are there any questions on this problem? And you could always check it. If we had unlimited time in here, I would take the derivative. Remember, we're claiming that this is my original function. So if I did my chain rule, my power rule with chain rule, I should get this integrin back, because remember that was my derivative and we're just reversing this process. So it's really good practice to check that. Just take the derivative real quick using your chain rule and see if you get the original integrin back. Okay, so technically you had all the tools you needed to be able to do this problem based on what we covered in class yesterday. What made this problem tricky is that there was a constant we needed to pull out from the beginning. And then we created a constant when we took the derivative of u that we needed to pull out again. So we had to pull a constant out twice. That was kind of a tricky aspect to this problem you hadn't seen yet. Okay, and the next problem we're about to do is brand new as far as the concept goes. So let's take a look at it. Ooh. See a square root. I also see a fraction. Well, let's just start by rewriting that square root, because I know none of my rules have a square root, right? So let's just rewrite that real quick. Okay, so if I rewrite my square root, I'd have x over binomial to the 1/2 dx. And I'm going to write my, we know it's not the e to the x rule, right? So I'm going to rewrite my reverse power rule and my reverse ln of x rule. Okay. Well, it can't be the reverse ln of x rule, because remember there's an understood exponent of 1. So even if I made this binomial a u, the exponent would not be a 1. So if the exponent is not 1, I can't use my reverse ln of x rule. So I must be trying to use my reverse power rule. Okay, so we need to rewrite this with a negative exponent to make it work. So let me do that real quick. So we are going to use some algebra. I'm going to take this denominator and relocate it to the numerator. Okay, so we have that now. You should ask yourself, can I distribute this x? Because if you can distribute the monomial into the binomial, our lives will be so much easier. But can I do it? No, it's not a plain binomial, right? If there was not that negative 1/2 there, yes, you could. But because we have this negative 1/2, I cannot distribute. So, okay, the easy way out is off the table. So that's a bummer. Okay, well, then we know the other tool in our tool belt is u substitution, right? So let's make our base the u. So we're going to make this my u, this base right here. So we're going to let u replace the x plus 2. So let's see what that would look like. That'd be x times u to the negative 1/2 dx. Hmm. Hmm. Well, okay. Let's go ahead and rewrite it where our x's are together. I'm just going to group this x back here with the dx. Let's go ahead and rewrite that. Still not looking great here. So that's okay. We know we need all u's, right? Right now I have x's, I have u's all mixed up. So let's go ahead and do our derivative because we know that's what we do here, right? So derivative of u with respect to x. So x plus 2 is a linear binomial. It's in y equals mx plus b format. So I know the slope is just 1, right? Or if I take the derivative of x, it's 1. If I take the derivative of a constant, it's 0. So I'm just going to end up with a 1 over there. Oh, okay. Let's move our dx over. So du swaps out for 1 dx. Well, do I need that understood 1 there? No, right? So du swaps out directly for dx. If I see a dx, I can swap it for a du. If I see a du, I can swap it for a dx. So over here, here's my dx. That's going to swap out directly for a du. And now look what we got. Okay. What's the problem? The problem is, do our variables match? No, I still have an x in there. What are we going to do? Here, let me write a little note here. What's the problem? We still have an x. We still have an x. So, we need to turn it into a u, right? We need x to swap out for something with a u. So what are we going to do? Well, we have a u, don't we, over here? I made up this, I established this rule. If I have a u, I can swap it for an x plus 2. If I have an x plus 2, I can swap it for a u. I made that, I set that in stone. So what we're going to do is we're going to take that and we're going to solve for x. So I'm going to take that u equals x plus 2, and I'm just going to solve it for x. I'm just going to isolate the x. I'll just subtract the 2 on both sides. So u minus 2 is equal to x. So now whenever I see an x, I can swap it for a u minus 2. So now when I see this x here, I can swap this x for a u minus 2, and then I'll have just u's. I know that's a lot, so I'm going to pause for a minute. Are there any questions? I call this double u substitution. I just make that up because I feel like I'm using the u twice, right? So in my brain, I call this double u substitution. I don't know what the technical term is, but basically I had to use the u twice. I had to use it in my base, and then I had to rewrite it to use again for this x. So I call this type of problem a double u substitution. I really should see if it has a real name. Okay, so let's go ahead and make that u substitution then. So I'm going to have the integral of u to the negative 1/2, and then the x is getting replaced with u minus 2, and then I have a du. So I have all u's. It's still pretty nasty, but at least I have all u's, right? but hopefully your brain will see that your binomial has an understood 1 exponent. So you are allowed to distribute this 1/2 into the binomial. And that's going to make this problem way easier because then you'll just have 2 terms. You can take the integral of each term separately. So let's go ahead and distribute that and let's see what we get. So remember, for your algebra rules, when you're distributing, when you're multiplying the same base, you add the exponents. So technically, I'm going to have a u, and I'm going to add the negative 1/2 to the understood 1 exponent there, minus, and then when I distribute it to the constant 2, they're just side by side multiplying. This is just algebra. I've just distributed a monomial, and I use the rule, if you're multiplying the same base, you add the exponents. And then I can clean that up a little bit. So that's going to be u to the 1/2 minus 2u to the negative 1/2 du. And then we'll just split it to 2 separate integrals because each term just follows the power rule. And you don't have to split it to 2 integrals, but I'm going to. So one time I'm going to take the integral of u to the 1/2 du minus one time I'll take the integral of 2u to the negative 1/2 du, and we'll see what we get. So go ahead and try that on your own. I'm going to shrink this, and then we'll check your answer. Okay, so hopefully you just applied that reverse power rule. You're increasing your exponents by 1, dividing it off. So I'm just going to do that over here real quick. And then technically the only step you need at the end is to unsubstitute the u. So u was originally an x plus 2. U was originally an x plus 2. So we just need to unsubstitute those. And then I suggest cleaning up the fractions a little bit. But my math lab was counting it right. So you technically don't need to, but I'll do both. So when I unsubstitute my u, I get all this stuff, which is mathematically fine. It's just, if this was a word problem, like in a minute we'll see a word problem, it would be really hard to plug in an x and like type all that into your calculator. It would be, you'd have to be really, really careful with how you enter things. So you can clean this up. There's an, let's look at this first term here. How can I clean that up? There's an understood 1 in the numerator. So on my calculator, I could just type 1 divided by 3/2. And that's going to change just to a 2/3. So I could erase all that and put a 2/3 in there. I'll just shrink it to do that. Give me one sec. Okay, so it would look like this. I would have a 2/3 x plus 2 to the 3/2. Minus, and then I'll do the same thing on the next one, 2 divided by 1/2. So 2 divided by 1/2 is just 4. x plus 2 to the 1/2. That's just way easier to calculate with. If I'm inputting a number to find an output, that's just a lot easier to type. But I don't know, show me a status. How do you feel now that you've seen this? It's okay to still be shocked, but just how do you feel about this sucker? I don't really, I prefer it to be what's boxed in with the simplified fractions, only because if this was a word problem and then you had to use this for a certain input, figure out an output, or vice versa, it's much easier to type in your calculator. But I'll accept either one correct, and MyMathLab will too. So, so whatever you're most comfortable with, but I would practice going that extra step of simplifying the fractions. Yeah, so basically I prefer this one. So I'll put a happy face on that. Oh gosh, I promise that's happy. Oh, it's getting worse. No. Okay. Oh gosh, he looks angry. Okay, well, never forget that. Let's put a heart. I can kind of do a heart. Okay. And just heads up, if I'm ever grading your paper and I drew a happy face and it looks angry, I promise I didn't draw an angry face on your paper. It was supposed to be happy. Okay, let's try another one of these. We can do everything scary the first time you see it, y'all. Everything scary the first time you see it. So let's look at another one. This one doesn't look scary at first. Like, it's obviously a power rule, right? I don't see a fraction. I don't see an e to the x. So it's obviously my reverse power rule. So I'll put my generic rule on here. Okay. Well, I know my base needs to be a plain variable. Here's my base, so let's make that my plain variable. Okay, so now I'm going to look like this. Okay, so I'm going to be quiet for a minute, and I want you to try this, because try to get the variables to match. If you try and mess up, that's okay, because then you might know what to ask me when I work it out. So I'm going to be quiet for 2 minutes. Okay, was that like the longest 2 minutes of your life? Okay, let's see. Let's see how you did, guys. Let's see. Okay, so usually this is the step people get to, students get to, and then they're like, okay, what? what? So whenever you feel that, like, hey, I know what rule I'm supposed to use. I did my u substitution. And then you're like, okay, I even took the derivative of the u. So I did all of this. And then I saw, okay, du swaps out for dx. Great. I come over here to my dx. I swap that out for my du. Okay, and then I have x u to the 8th du. And then you're like, what? My variables don't match. Okay, when you get to that point where you're like, what? That's double u substitution time, y'all. You're just using what you have, right? So what do I have? I need x's. I mean, I need u's. Do I have an x somewhere? Well, I do, kind of, right? Up here. You're going to come up here and do this double u substitution. So you're going to take that and solve for x. Solve for x. So u equals x plus 6. Subtract the 6 on both sides. So anywhere I see an x, I can replace it with this binomial. So over here where I see an x, I'm going to replace it with a binomial u minus 6. Okay, so let me go ahead and do that. I'm going to have u minus 6, u to the 8th, du. And it's still hideous, but did you notice? that your binomial is just a plain old binomial exponent of 1, so you can distribute that monomial to both terms in the binomial. So when you do that, you end up getting a u to the 1 plus 8, so that would be a u to the 9th, minus a 6u to the 8th, and all of that is my integrand. So let me pause here to see if there are any questions about this double u substitution that I did. Show me a status. How do you feel about this needing double u substitution? Still a little shocked. Some people happy. Trinity, go ahead.
So I know this is probably just like basic algebra,
Mhm.
but whenever you're like distributing the u to the 8 to the u minus 6, whenever it's so you just because they have the same base for the u, it
Mhm.
just like adds on. I guess I forgot that. I don't know.
No, it's okay. So like when you have, I'm going to rewrite it this way because that's what we're more used to seeing. When I'm distributing a monomial into a binomial, what's happening is distribution is a form of multiplication. So this is technically u to the 8th times u minus, then I distribute it to the second term. That's technically going to be like u to the 8th times 6, right? It's just multiplication. But we have a rule in algebra that says if your bases are the same, so see how they're both u's, you just add the exponents. So you keep the base the same and you add those exponents together. Whereas in the other term, when I had u to the 8th and 6, like there's technically an understood 1 in front of that u. So technically on this one, you're multiplying the coefficient 1 and this coefficient 6. They're not like the same base. And that's, I just rearranged the order of the multiplication. I put the coefficient first and the variable term second. But yeah, it's just this idea of when you're multiplying the same base, you add the exponents.
Okay, yeah, that helped a lot. I just forgot. Thank you.
It's okay. Whenever a student struggles in calculus, 90% of the time it's with the algebra, like having to dust cobwebs off algebra. It's hardly ever with the calculus. It's the algebra that gets you to the calculus or the algebra that happens during the calculus or after the calculus. But okay, cool. And then once you get to this point, you can just separate this into two integrals. So I can take the integral of the first term minus the integral of the second term. So go ahead and do that if you haven't done it yet. Okay, so that's u to the 10th over 10 minus 6 u to the 9th over 9. Okay, and then we just have to unsubstitute those u's for u for x plus 6. Oh, I erased one of my equal signs there. Made it look like a negative. Okay, so then we would just have a 1/10 u to the 10th minus a 6/9. My MATLAB might make you reduce that one. Because 6/9 technically reduces to 2/3. I don't know, but I don't know. It might count it. I don't know. It might let you. If you get it wrong, make sure you just before you assume you did everything wrong, just double check your fraction to see if it could reduce. I would count it right on a test, but my MATLAB is a computer and it's been programmed usually to reduce fractions, but it's been surprising me lately. Okay, cool. God, I want to check this one so bad, but I want to make sure we finish the word problem. No one else is compelled to take the derivative of this to see if it matches the original integrand? No, just me? Dying to do it, but I'm resisting the urge. Okay, So did I do that right? Can anyone confirm my answer? Did anyone else get this? Cool. Yes. Okay, cool. I do not trust my brain today, y'all. Okay. Okay. We just have, I think there's just one problem left, right? A word problem? Ooh, if we finish this and have extra time, we'll come take the derivative of one of these just to practice that skill because I'm thinking on test 4. So, it's split over 2 days. One day we're going to focus on test 5 material. One day, one day we'll focus on chapter 5 material and the next day chapter 6 to kind of help you study. But the cumulative aspect, I think, is just going to be checking your answers by taking the derivative. So if we have time, we'll come back and check that one. But here we go. Okay, word problem time. Dun, dun, dun. Let's take a look at it. Here we go. Okay, let's read this sucker. It says the marginal price. So I'm going to stop right there and just remind myself, marginal, when you hear the word marginal, that means derivative. So marginal price is going to be P prime, right? Marginal price. So the marginal price at a supply level of X bottles of shampoo per week. So X is representing the number of bottles of shampoo per week. Okay. Is given by this function. Find the price supply equation if the distributor of the shampoo is willing to supply 75 bottles a week at a price of $5 per bottle. So that, remember, a price supply equation links a demand with a price or a price with a demand. So they're saying if the demand is 75 bottles a week, then the price will be $5. Or if the price is $5, then the demand will be 75 bottles per week. Like those are linked together. So that's a clue that we'll probably use later. And then we're being asked a question. How many bottles would the supplier be willing to supply at a price of $5.15 per bottle? Okay. Oh, and we're also being asked to find the price supply equation under those conditions. Okay, so we got a lot of stuff to do. So right now we're given the marginal price supply equation. We need to go back to the original price supply equation. So right now we're given P prime of X, but if I take the integral of it, it's going to give me a general price supply equation back. It'll have that generic plus C in it, right? So let's go ahead and do that. Let's find that integral. Okay, I see a fraction. So I'll give you a second to figure out which rule we should be using. Okay, well, hopefully you notice that we're not going to do the ln of x rule because for the ln of x rule, we'd have to have an understood exponent of 1. And right now my exponent is not a 1. Is not a 1. So we're not going to do the reverse ln of x rule. We need the reverse power rule. So we're going to relocate that whole base to the numerator. And we're going to follow our reverse power rule. Okay, so I'll be quiet for a minute. I want you to try this. Okay, so hopefully you got a chance to start this one. I know you didn't finish it, but for sake of time, I want to make sure we move on here. But hopefully you recognize that your base needed to be your u. And so you took the derivative of the u with respect to x and you got 3. So du cashes in for a 3 dx. But we don't have a 3 dx there. We have a 300 dx, right? It's like, So there's lots of things you can do, but most typically we'll just take that 300 out because it's not what we need, right? We need a 3. So I'm going to take that 300 out. And then right now, if I just did my u substitution, I'd end up with a u to the negative 2 and a dx. If I just took the 300 out and I just replaced my base with a u, this is what I'd end up with, but my variables didn't match. So then we're going to use this idea that if I can get this dx alone, that's what I have, I can swap it for something with a du. So we're just going to divide both sides by 3. So I divide by 3. That's going to end up being a 1/3 du. So that dx is going to cash in for a 1/3 du. So if I rewrote it, it would look like this. 300 got pulled out, u to the negative 2 times a 1/3 du. But then again, we have that constant fraction that we can pull out to the side, and it'll be side by side multiplying with the constant that's already there. So you end up with 100 on that one. So my integral looks like this, 100 integral of u to the negative 2 du. Awesome, and that's set up to use our reverse power rule. So let's go ahead and use that. So you'd end up with u to the negative 2 plus 1 over negative 2 plus 1 plus c. Okay, now I can clean that up. Oh, I need to shrink some stuff down. Hold on real quick, y'all. Are there any questions with what I've done so far while I'm shrinking? Okay, let's go ahead and finish cleaning this up. So that would be 100 u to the negative 1 over negative 1 plus c. And then I'm going to do a couple things. I'm going to unsubstitute this u, and I'm also going to divide the 100 by the negative 1 just to clean that up a little bit. So I'm going to get negative 100 u to the negative 1 plus c. What was u again? 3x plus 25. 3x plus 25. Okay, and this is my generic price function. Remember, we had marginal price, and now we found the generic price function. Okay, so let me pause right there. Show me a status on how you feel about reversing that marginal price. Remember, this was our P prime right there. Reversing that P prime to get my just P function back, my price demand function back. Show me a status on how you felt about this process. Okay, a lot more happy faces than last time, but not everyone's happy, and that's okay. Remember, the real learning happens outside the classroom. Okay, but we're not done yet because we just found a general price supply equation, right? This is the general price supply equation. And the reason why it's a general price supply equation is because we still have this generic plus c there. We have a generic plus c. So we need to use some information that was given to us to figure out what that c really is under the certain conditions. So what conditions were we given here? Let's go back and look. What? Oh, we were told right here that they were willing to supply 75 bottles at $5 per bottle. So that information is tied together. If it's 75 bottles demanded, it's $5 per bottle. If it's $5 per bottle, 75 will be demanded. So we're going to kind of use that information. We just have to figure out what our input and output is. So remember, we're inputting an X. X was the number of shampoo bottles per week, right? So we're going to input the number of bottles, and we're going to output money. We're going to input number of bottles because that's what my X was. Up here, X was number of bottles. And we're going to output the cost per bottle. So we're going to input 75 bottles and we need to output $5. So let's go do that and see what C would have to be. So I'm going to input 75 and follow my new rule, -100. Let me zoom in a little bit. How am I going to, there's no way I'm going to fit that. Here, let me add a page. There's no way that's going to fit. Let me add a page. Okay, this will be better. Let's do it down here. Yeah, whenever you see a whole page for a problem, you should be very afraid, right? Okay, so I'm inputting a 75. Everywhere I see an X. And I need to output $5. So we're just going to do some algebra here. It's not that bad, right? This one is pretty straightforward. We're just going to enter all this in your calculator. And let's see what we get when we do that. Okay. Oops. -40 cents. So when I put all this in my calculator right there, I ended up getting -0.4 plus C equals $5. So if I want to figure out what C is, I just need to add 40 cents to both sides. Okay, so my constant's going to be $5.40. So instead of having this general equation, now I'm going to have a specific price supply equation. And this is it. It's going to be -100, 3x plus 25 to the -1 plus $5.40. Oh my gosh, it's messy. So that was one of the things we were asked to find. We were being asked to find a specific price supply equation under those conditions. So we found that. Any questions on how we use that pair of information, that input and output, to get the specific value of C? No? Okay, now we got to use that sucker to find what? I already forgot. Let me come back up here. So, so basically we just did this right here. Find the price supply equation if, so we found that. So now we're being asked how many bottles, so we're looking for X, how many bottles, X is the number of bottles, are they willing to supply at a price of $5.15? Okay, how many bottles are they willing to supply? So basically we need to figure out my input that would create a price output. So what would I have to plug in to get a price of $5.15 out? Okay, that's what this is asking. So let's go ahead and try that. So it's going to involve some algebra. And this is the same algebra from the 5.1 notes that we didn't have time to do with the exponents. I kind of talked about it briefly, but now we're going to see it in action. So let's go ahead and do that. So what input will create an output of $5.15? Okay, here we go. So basically, I'm going to take my specific equation. So the specific equation, I'm going to rewrite it here. Okay, and it's asking me what number of bottles would I have to input to create an output of $5.15. So basically, I'm just going to end up solving this equation. So let's go ahead and do that. We're just leaving the x in there because x is an input, right? Okay. So if we're just doing basic algebra now, if we want to get this x alone, I need to get this whole term alone first, right? This entire term, I need to get it alone. So the first thing I need to do is subtract off the $5.40 from both sides. And that came out to be negative 25 cents. Okay. I'm still trying to get this x alone. X is part of this binomial. So I need to get this binomial alone. The binomial is currently being multiplied by a negative 100. So I need to divide by a negative 100 on both sides. Okay, so now I'll have the binomial to the negative 100. I need to divide by negative 100. So that would be positive 0.0025. Okay, I'm still just doing algebra. I need to get to this x. Oops. Still need to get to this x. It's being trapped in this binomial, so I need to get rid of that negative 1. And this is the trick, the algebra trick we kind of talked about last class, about how I can do anything to the left-hand side besides multiply by 0 as long as I do it to the other side. So like I could square the left-hand side as long as I square the right-hand side, but squaring isn't very helpful. What do I want? Think about your goal. Your goal is to have a binomial with a 1 exponent, because then I don't really need to write it. Then it would just be the binomial by itself, right? So my goal is to get a 1 exponent there. So I want to raise the left-hand side to an exponent that will create a 1. So if I raise it to the negative 1 power, is it negative 1 times negative 1? A positive 1? Yeah. Technically you're multiplying by the reciprocal of that, but the reciprocal of negative 1 is negative 1. Like the one we saw before, we had something like this. Like say you had a binomial to the 2/3 power. In your previous summer, you raised that to the you raised it to the reciprocal. And then when you multiply that, it gives you 6/6, which is just a 1. Like your goal is always to get an exponent of 1 here. This one's just a little bit weirder because the reciprocal of negative 1, if you make it a fraction and you flip it around, it's still going to be just a negative 1. But yeah, it's that idea of, since you can raise it to any power you want, raise it to the reciprocal, and then it'll create that 1 exponent there. So just a little algebra trick that we use a lot to simplify this. There's other ways to do it, but that's the easiest way. So if I raise the left-hand side to the exponent negative 1, I need to raise the right-hand side to the exponent negative 1. And on the left-hand side, it'll give me an exponent of 1. On the right-hand side, it'll give me, I don't know, give me 1 second. 400? Okay, and now that we have a binomial to the first power, we don't really need those parentheses anymore. Now it's just super basic algebra. You're still trying to get to this x, so you need to get the 3x alone, so just subtract the 25 on both sides. Okay, and you're still trying to get the x alone. It's being multiplied by a 3, so divide by 3 on both sides. And we get 125. And because it's a word problem, you can't just stop there, and you have to put units, right? What was X representing again? The number of bottles. So you need to use that unit. This would be 125 bottles. And you would say something like, at a price, or I could say they are willing to supply 125 bottles at a price of $5.15 per bottle. Oh my gosh, we finished right on time. It's a miracle. So the main idea in this problem is there wasn't anything new. We're just combining all these ideas together. And remember, any word problem, you got to slow your brain down and say, what is the input? What is the output of this function? What am I inputting into the function? What am I outputting from the function before you can solve it? And that goes for any word problem in this class that has a function involved. Okay. So I know class is technically over. You can finish your 5.2 homework now. You can finish the 5.2 homework. And then next class, we're going to hopefully do a streamlined 5.4 and 5.5 set of notes. Okay, y'all. You survived another class. Y'all are good to go. I'll hang around if you have questions. Oh, there is a take-home quiz. Thank you, Trinity. I need to post it. Y'all, there will be a 5.2 take-home quiz, but it won't be due until Tuesday. I'm going to give y'all a week to work on it, so it won't be due next class. But thank you. Yes, I will post that on the calendar right now. Yeah, I mean, I know these are harder, so I'm giving you a whole weekend to work on it. I'm going to do that right now. I already have it written.